Have you ever just stopped and wondered how your computer, your phone, any of it, can perform millions of calculations in literally the blink of an eye? Well, it's not magic. It's logic. Incredibly simple, lightning-fast logic. Today, we're going to pull back the curtain and look at the fundamental building blocks that power our entire digital world. So let's dive in.
All right, here's the game plan for our journey. We're going to kick things off with the most basic concept, circuits that live completely in the present moment. From there, we'll see how they learn to do math, make decisions, and even act as translators. And finally, we'll see how all these simple little pieces combine to create the incredibly complex systems that we use every single day.
So, first up, let's talk about the absolute foundation of everything. We're talking about circuits that make decisions based only on the information they have right now. There's no past, no memory. This makes them ridiculously fast and totally predictable.
And this right here is what we call a combinational circuit. You can think of it as a pure, instantaneous logic machine. There's no what if or what happened before. It's just a direct, immediate reaction. What goes in right now determines what comes out right now. And that's the key, because this allows for those mind-bogglingly fast operations. We're talking millions, even billions of times every second inside your devices.
Now, building these things isn't just guesswork. It's a really precise, methodical process. Engineers start with a problem, they map out every single possible scenario in what's called a truth table, and then they simplify it all down to the most efficient design possible. This step-by-step procedure is how we can build reliable, complex logic from the ground up.
Okay, so we've got the basics of these instant decision circuits down. Now let's get to something we can all relate to: doing math. I mean, how does a machine that's really just made of a bunch of on and off switches actually, calculate anything?
Well, believe it or not, it turns out that everything, from the complex physics in a video game to the calculator on your phone, it all boils down to this one fundamental operation: adding ones and zeros. The circuits that handle this are called binary adders, and they are the absolute heart of a computer's number-crunching brain.
And what's really brilliant here is the efficiency. You don't actually need a totally separate circuit just for subtraction. See, with a clever little trick involving flipping the bits and adding 1, engineers can make a binary adder also perform subtraction. It's just a perfect example of the elegant simplicity that's at the core of all digital design.
So our circuits can now do math. That's great, but a computer's real power isn't just in the number crunching. It's in its ability to make decisions based on those numbers. Exactly! This is the next critical piece of the puzzle. For a computer to be actually useful, it needs to be able to compare different values and then choose a path based on the result. But how does it do that on a hardware level?
Well, the answer is this little guy, the magnitude comparator. It's a circuit built for one specific job. It takes in two numbers, A and B, and then spits out one of three simple signals. A is bigger than B, A is smaller than B, or A and B are equal. This is the fundamental building block for every single if-then statement in software.
Okay, so once a decision is made, you need a way to actually route the correct data, and that is the job of a multiplexer, or MUX for short. It's got multiple data inputs coming in, but only one output going out. You can think of it exactly like a train track switcher. It uses select lines to act like a lever, choosing which one of the inputs gets to go through to the output, while all the other data streams have to wait their turn.
And as you might guess, there's an opposite. A demultiplexer, or a demix, does the exact reverse. It takes one single stream of data coming in, and based on its select lines, it directs that data to one of many different destinations. So when you put them together, the MUX and demux are basically the traffic cops of the digital world.
All right, so we can calculate, we can compare, and we can route data. But different parts inside a computer often speak in different digital codes. They need translators to be able to understand each other.
And that brings us to decoders and encoders. A decoder takes a compact binary code, let's say the number 3, and it activates one specific output line, in this case the third one. An encoder does the exact opposite. So when you press the letter G on your keyboard, an encoder is what takes that one single physical input and turns it into the binary code that the computer actually understands as G.
This table is a perfect example of a priority encoder in action. Just look at that bottom row. If input line Y3 is active, it doesn't matter what the others are doing. The X's mean don't care. The output is always going to be binary 1-1. It gives priority to the highest numbered input, which is absolutely crucial for handling situations where multiple things are happening at once.
Beyond these two, there's actually a whole family of circuits just called code converters. And their entire job, really, is just to translate from one digital dialect to another, making sure all the different parts inside a complex system can communicate with each other perfectly.
So we've seen all the individual pieces of the puzzle. Now for the really cool part, let's put it all together and see how these simple, elegant little blocks create the powerful systems we all rely on.
This quote from the legendary computer scientist Edsger Dijkstra just says it all. The real genius isn't just in making the individual blocks, it's in how we combine them to manage and organize an insane amount of complexity.
And that's the key takeaway here. None of these circuits exist in a vacuum. They're like Legos. You combine basic adders to build a brand new circuit that can multiply. You take those same adders, add some other logic gates, and you get a special adder that can work with decimal numbers for your calculator. You can even use a multiplexer as a sort of universal logic block to create almost any function you can dream up.
And this stuff isn't just theory. It is everywhere. The comparator, the adder, the multiplexer, that's the very heart of your computer's CPU. Decoders are what help your computer find the right piece of memory. Encoders read your keyboard. These components are truly the invisible, unsung heroes of all modern technology.
So, we've gone all the way from a simple, memoryless circuit to the essential components of a CPU. We've seen how just a handful of logical ideas, when organized with incredible precision, can create a world of unbelievable complexity and power. It all starts with these simple blocks. The only real question left is, what are we going to build with them next?